1,800th of our sun's brightness, cold, ancient, and seemingly unremarkable. But hidden beneath that stillness was a cosmic jackpot unlike anything found before. One by one, astronomers picked up tiny dips in its light, signals of planets passing in front of the star. Soon, they realized they weren't viewing a single habitable candidate, or even just a few. They had uncovered an entire family of Earth-sized worlds. 7 rocky planets orbiting closer to their star than Mercury orbits ours. Each is locked in such a tight gravitational embrace that the same face of every planet is permanently fixed toward the star. Initially, many experts wrote the system off as hostile. Red dwarfs are infamous for violent magnetic storms, extreme flares, and chaotic radiation that can rip atmospheres to shreds before life ever gets a start. Yet, TRAPPIST-1e refused to be ruled out. Its orbit puts it in the exact center of the star's habitable zone, soaking up about 2/3 of the light Earth receives, an amount just right to sustain liquid water, if, and only if, the planet manages to cling to a stable atmosphere. That question became the driving force behind one of the most ambitious observation campaigns in exoplanet science history. Because TRAPPIST-1e isn't just another rocky planet. It is the single most promising Earth-like world ever discovered around another star. When NASA awarded early observation time on the James Webb Space Telescope, the DREAMS collaboration, a team with guaranteed access, made an immediate choice. They aimed the world's most powerful telescope straight at TRAPPIST-1e. Their goal was simple yet audacious: determine if this small, distant world possessed an atmosphere at all. To achieve this, they utilized transmission spectroscopy, a technique so delicate it relies on measuring how a planet's atmosphere filters tiny slices of starlight during a transit. For most exoplanets, this is nearly impossible. But TRAPPIST-1 offered a unique advantage. Because the star is so dim, any planet crossing its face blocks an unusually large percentage of light, creating a signal far stronger than we would ever see around a sun-like star. Webb's NIRIS instrument recorded the wavelengths absorbed during 4 separate transits of TRAPPIST-1e. The initial data eliminated several possibilities immediately. The planet does not hold a primordial hydrogen-helium atmosphere. Radiation from the red dwarf would have blown that away eons ago. It doesn't have a thick, Venus-like carbon dioxide blanket, nor a thin, dying atmosphere like Mars. All those scenarios were ruled out. What remained was the possibility that TRAPPIST-1e holds something far more compelling: an Earth-like atmosphere dominated by nitrogen, with greenhouse contributors like methane, water vapor, or carbon dioxide in smaller, life-supporting amounts. If such an atmosphere exists at roughly 1 bar of pressure, similar to Earth's, it would be fully capable of moving heat to the dark side of this tidally locked world, allowing a global ocean to persist beneath skies forever split between eternal day and endless night. This was the moment scientists began to whisper, cautiously, that this world might be more than habitable. It might be alive. However, an atmosphere alone doesn't guarantee life. Being so close to its star, TRAPPIST-1e is almost certainly tidally locked, meaning one side faces perpetual daylight while the other is trapped in frozen darkness. The question scientists raced to answer was whether the world could distribute heat well enough to avoid catastrophic extremes. Webb's data provided clues, but not certainty. If the atmosphere is dominated by methane, the greenhouse effect could invert, cooling the surface and restricting liquid water to the daylit side only. Instead of a global ocean, TRAPPIST-1e might host a hemisphere-bound sea, the kind of environment where prebiotic chemistry could bloom in warm pools beneath a red-orange sky. Simulations have even suggested that life could thrive along the Terminator, the thin ring of everlasting twilight separating day from night, a narrow but stable climate strip known as Terminator habitability. Others have proposed an even more exotic scenario: TRAPPIST-1e as an icy volcanic world with a subsurface ocean similar to Enceladus or Europa. On such a world, Hydrothermal vents could serve as cradles for emerging organisms, just as some scientists believe happened on early Earth. Regardless of which environment is real, the implications are profound. TRAPPIST. One, he may not be a simple Earth clone. It might be something stranger, more varied, and more alien, yet still absolutely capable of sustaining life. And the chemistry Webb detected only deepens the mystery rather than solving it. Of all the factors defining TRAPPIST, 1E's chance at life, none is more dangerous or essential than the star it orbits. TRAPPIST. 1 is a volatile red dwarf whose flares dwarf anything our sun produces. The strongest geomagnetic storm in Earth's recorded history, the Carrington event, would be a routine occurrence on TRAPPIST. 1, happening every 2 days on average. Such storms unleash torrents of radiation capable of stripping atmospheres away molecule by molecule, potentially turning worlds into barren rocks even after life begins and oceans form. Paradoxically, however, those same flares might be necessary for life's origin. UV radiation plays a critical role in forming the building blocks of RNA, the fundamental molecules behind every organism we know. TRAPPIST. 1 is far calmer today than in its violent youth, offering a potential window where life could emerge and persist, provided the planet has some protection. And TRAPPIST. 1, he might indeed have that protection. A molten iron core could generate a magnetic field strong enough to shield the atmosphere, especially with tidal forces constantly kneading the planet's interior and injecting heat. Much like Jupiter's moon Io, which is sculpted into perpetual volcanic activity by gravitational stretching. Combine a magnetic field, an atmosphere, a heat distribution system, and potential water, and suddenly the odds tilt toward a world that is not only habitable, but shockingly resilient. Yet, Webb's data cannot confirm the ultimate truth just yet. TRAPPIST. 1, it could be a thriving ocean world, or a frozen, airless marble condemned before it ever had a chance. What Webb has confirmed is that this world is unlike any other we have studied, and its probability of supporting life, based on every known metric, makes it the most promising candidate humanity has ever found out of TRAPPIST. 1E truly possesses an atmosphere. Its very existence would be a small miracle. While TRAPPIST. 1 is dim and ancient, it remains a red dwarf, one of the galaxy's most temperamental classes of stars. These stars erupt with ferocious flares, magnetic storms powerful enough to dwarf anything our sun has ever produced. In fact, the worst geomagnetic event in Earth's history is estimated to occur on TRAPPIST. 1 every 2 days, a staggering rhythm of destruction that would bombard any nearby planet with torrents of charged particles. If TRAPPIST. 1E orbits so close that its star appears 4 times larger in the sky than our sun does from Earth, the atmosphere must withstand a cosmic onslaught happening almost in real time. This raises the question, how does a world survive such fury long enough for life to take root? Red dwarfs have extraordinarily long lifespans. TRAPPIST. 1 will shine for 10 trillion years, far longer than the current age of the universe. But these calm twilight eons only arrive after a violent, destructive youth. If TRAPPIST. 1, he tried to form a secondary atmosphere during this stormy era, the star might have stripped it away before it ever matured, leaving the planet barren and airless. And yet, James Webb's ambiguous signals suggest something else might be happening. If TRAPPIST. 1, he does still hold an atmosphere, then it survived odds that should have erased it billions of years ago. That alone would push the probability of life far beyond random chance. Survival itself becomes evidence. Even if the surface of TRAPPIST. 1E is cold or partially frozen, the planet may hold a secret advantage deep beneath its crust, tidal heating. Due to its close and potentially eccentric orbit, TRAPPIST. 1E is squeezed and stretched by the gravitational pull of its neighbors in the 7-planet system. This constant flexing injects internal heat into the planet, heat that could fuel volcanism, magnetic activity, and even subsurface oceans. The research compares this phenomenon to Jupiter's moon Io, the solar system's most volcanically active body, a world whose interior is pumped with energy simply by the gravitational tides of its siblings. TRAPPIST-1e may experience a similar mechanism, generating an estimated 0.18 watts per square meter of internal heating, 24 times more than Earth receives from tidal forces. This isn't merely a geological curiosity. Internal heat can keep water liquid beneath an icy shell, drive chemical reactions, and support entire ecosystems without sunlight, just as hydrothermal vents sustain life in Earth's deepest oceans. If TRAPPIST-1e has volcanic activity, it could continuously replenish atmospheric gases like carbon dioxide, methane, or nitrogen, gases that James Webb is specifically hunting for. Tidal heating could, therefore, be the planet's heartbeat, a hidden engine keeping it alive even when starlight fails. There's a strange paradox at the heart of the TRAPPIST-1 system, a contradiction that might decide its fate. The star's violent flare activity could easily sterilize surfaces and strip atmospheres. Yet, that same radiation is believed to be essential for the creation of life. On Earth, ultraviolet light played a critical role in forming RNA building blocks, the molecules that allowed early life to metabolize, replicate, and grow. In other words, without a certain amount of stellar violence, life as we know it might never have emerged. TRAPPIST-1e sits at the intersection of these two forces in a narrow balance between destruction and creation. Red dwarfs eventually calm down, entering long, stable phases with drastically lower X-ray and UV output. TRAPPIST-1 is now in that stage, meaning the planet may finally have the quiet stability needed for life to persist. But the question remains, did an atmosphere survive long enough to benefit from this calmer era? The data suggests a promising possibility. If TRAPPIST-1e developed a magnetic field comparable to Earth's, generated by a molten iron core and enhanced by tidal energy, it could have shielded its atmosphere for billions of years. This would position TRAPPIST-1e as a rare world that endured the worst and emerged as a stable, life-capable planet. A world forged in extremes that may have unintentionally created the perfect conditions for biology to rise. James Webb has delivered the first hints of TRAPPIST-1e's atmospheric composition, but the documentation makes it clear the real breakthrough hasn't happened yet. Scientists have already scheduled 15 additional transits before December. Each one allows Webb to collect more precise spectral data, refining the fingerprints of molecules in the planet's atmosphere to push the noise floor lower and lower until doubt collapses into certainty. These transits are not routine observations. They represent the most ambitious campaign ever undertaken to characterize the atmosphere of a rocky exoplanet orbiting a red dwarf. If Webb detects methane, carbon dioxide, or nitrogen with consistent signatures, it will confirm the presence of a secondary atmosphere, a monumental step in assessing habitability. If water vapor is detected, even in small quantities, the implications could be historic. And if the spectral patterns match those of a stable, Earth-like atmosphere, then TRAPPIST-1e will become the most compelling life candidate ever found. But the suspense isn't only scientific. Each transit deepens the tension. Will this planet be revealed as a cold, dead sphere, or as a living world with oceans, climates, chemistry, and perhaps biology evolving beneath a dark red sky? Humanity may be months away from the first true confirmation of life outside Earth, or from the realization that we came heartbreakingly close, but not close enough. Either way, TRAPPIST-1e is no longer just a distant planet. It is a mirror held up to our deepest question: are we alone? One of the most extraordinary and unsettling aspects of the TRAPPIST-1 system is the sheer age and longevity of its star. Red dwarfs are the slow burners of the cosmos, consuming their fuel so gradually that their total lifespan can reach 10 trillion years, a number so vast it makes the universe's current age of 13.8 billion years feel almost insignificant. TRAPPIST-1 has already survived its volatile youth, the chaotic period during which extreme flares could have stripped atmospheres, sterilized surfaces, and reshaped the planetary system. Yet, that immense longevity means planets like TRAPPIST, 1E could theoretically host life for billions upon billions of years, far longer than Earth will ever have. Even if the planet lost its first atmosphere early on, the timeline available for regeneration, regrowth, and geological recycling is unimaginably long. This makes TRAPPIST, 1 a world where life, if it ever emerged, would have more time than any Earth organism could dream of to evolve complexity, intelligence, or entirely alien biological systems. The paradox is haunting. TRAPPIST 1's greatest threat to life was in the distant past, yet its greatest gift is the nearly eternal stability that follows. And TRAPPIST 1E sits right in the middle of that unimaginable temporal ocean. Among the most fascinating details in the reports is the subtlety of James Webb's spectral readings. Data so sensitive that scientists must interpret it with extreme caution. TRAPPIST 1's early transit spectra show neither the deep signatures of thick carbon dioxide nor the unmistakable markers of a primordial hydrogen envelope. Instead, they reveal a faint, ambiguous pattern, a spectral silence that can only be explained by two possibilities. Either the planet is truly airless, or it possesses a dense, compact atmosphere dominated by heavier molecules that Webb is just barely beginning to detect from 40 light-years away. This ambiguity is precisely what makes TRAPPIST 1E so compelling. An atmosphere rich in nitrogen, like Earth's, would leave a very subtle fingerprint during transit, one that requires multiple consecutive observations to identify confidently. And that is exactly what scientists are racing to collect. This situation is unlike any prior exoplanet discovery. It is not the triumphant identification of water vapor or methane, nor a clear declaration of atmospheric collapse. It is a scientific cliffhanger, data balanced on a razor's edge where every new observation could swing the interpretation toward a living, breathing world or toward a silent, frozen one. The fact that TRAPPIST 1E's readings remain so difficult to classify may itself be the strongest hint yet that its atmosphere is something Earth-like rather than exotic or extreme. One of the most intriguing concepts raised by the tidal locking of TRAPPIST 1E is the possibility of a Terminator habitat, a ring-like region of perpetual dusk where conditions might be just right for life. On the day side, temperatures could soar beneath the unblinking red star, driving potential evaporation and intense heating. On the night side, darkness stretches forever, cold enough to freeze ocean solid. But in between lies a thin, dynamic boundary where the chill of deep night meets the heat from the star, creating a stable zone with temperate conditions similar to Earth. In this twilight belt, winds circulating between the hemispheres could maintain a stable climate capable of supporting liquid water and moderate temperatures. The research highlights that in several models, even a sparse water supply or limited atmosphere can lead to long-term climate stability right along this dividing line. Life in such a region would evolve in an environment unlike anything on Earth, neither light nor dark, but a world bathed perpetually in red-orange twilight. Plants, if they existed, would likely adapt to low light levels. Animals might evolve to navigate gradients of illumination and temperature rather than daylight cycles. TRAPPIST 1E may therefore host not a planet-wide biosphere, but a narrow ribbon of habitability, a cosmic equator where life clings to balance in a world split cleanly in half. Music. While much of the excitement around TRAPPIST 1E focuses on potential surface conditions, the documentation also opens the door to a completely different kind of habitability, a subsurface ocean similar to those on Enceladus or Europa. If TRAPPIST 1E is a volcanically active world with tidal heating pushing molten rock upward and fracturing the crust, it could easily sustain pockets of liquid water beneath layers of ice. On Earth, life thrives in such darkness, feeding on chemical gradients rather than sunlight. Some scientists believe life may have even originated in deep-sea hydrothermal vents. TRAPPIST One may mirror this environment, with volcanic fissures releasing mineral-rich fluids into an ocean sealed beneath kilometers of ice. What makes this scenario compelling is that subsurface oceans are naturally shielded from stellar flares, atmospheric stripping, or violent radiation. Even if TRAPPIST-1 lost its surface atmosphere billions of years ago, a thriving biosphere could still exist underground, completely insulated from stellar violence. This transforms the search for life. Instead of searching for spectral traces of gases, we may eventually need instruments capable of detecting cryovolcanic plumes or geothermal activity. TRAPPIST-1 could therefore be a world where life survives not because conditions are gentle, but because it has retreated into a protected sanctuary beneath the surface, waiting for us to discover it. In the end, TRAPPIST-1 stands as one of the most extraordinary worlds humanity has ever discovered. Not because it guarantees life, but because it refuses to let the question die. Every measurement, every spectral line, every transit observed by the James Webb Telescope pulls us deeper into a mystery that grows more compelling with each new piece of data. A world that exists in perpetual extremes, one half scorched by endless daylight, the other locked in eternal night, yet still finds ways, through ocean or atmosphere or tidal heat, to remain possible. A world orbiting a star so long-lived and ancient that it makes Earth's timeline look like the blink of an eye. A world that has endured the violent youth of a red dwarf, survived storms that should have erased it, and now sits in a delicate balance where life could emerge in volcanic oceans, twilight belts, or even global seas warmed by a hidden greenhouse atmosphere. What James Webb has shown us so far is not certainty, but potential. Potential so strong, so statistically remarkable, that TRAPPIST-1 now stands at the very forefront of our search for life. The absence of hydrogen, the ruling out of Venus-like carbon dioxide, the hints of heavier gases, the climate models revealing stability even in tidal lock. All of them point toward a planet that may have defied cosmic odds. And yet the danger is always present. Red dwarf flares that could strip an atmosphere to its bones, gravitational tides that could fracture a world from within, and timelines so immense that life might rise and fall before we ever detect it. TRAPPIST-1 could be a silent graveyard or a thriving haven, an airless sphere frozen in time, or a living world sculpted by twilight. But this is precisely what makes it breathtaking. For the first time in history, we are not staring at theoretical models with no observational anchor or distant gas giants or vague hints. We are staring at a real world. A rocky, Earth-sized planet 40 light-years away, whose atmosphere may be within our reach to confirm. A planet where chemistry could be stirring right now beneath red skies. A planet that may be writing its own version of life at this very moment. And with 15 more James Webb transits on the way, the answer is coming, slowly, quietly, inevitably. Maybe TRAPPIST-1 will disappoint us. Maybe its surface is cold, barren, and airless. Or maybe, just maybe, it will become the first world in human history where we can point and say, there, life exists there. And when that moment comes, everything changes. Our future, our science, our understanding of the universe and of ourselves. If you want to be here when those discoveries arrive, if you want to follow every atmospheric breakthrough, every James Webb update, every new clue about this extraordinary world, make sure to subscribe, turn on notifications, and stay with us. Because we are closer than ever to answering humanity's oldest question, and the next piece of the truth could drop any day now.